this follow-up goes with our water phase change lab, and we're going to be talking about what's happening with the thermal energy, the heat that we're using to cause the phase changes, and what's happening to the molecules in the water during these different processes. So first things first, here is the graph of the data that I gave you from that video we watched. So the temperature of the water in Celsius over time during heating. You can see temperature starts out at like -40-ish, and then it increases over time. But it has these two regions where it's actually quite flat. And so we're going to talk a little bit about why that's happening. Before we do that, please use blue to label all three phases of water observed. So you should have solid, liquid, and gas labeled. Then using red, label all of the phase changes on the graph with the arrows pointing towards the state of matter that the water changed to. So for example, condensation, which is a gas going to a liquid, right, would be this way. This would be condensation, be pointing towards the left, and this part would be liquid. So go ahead and take a minute, draw this graph in your notes, label the different parts, pause the video to do that, and then we'll look at it together. Okay, so here's your labels. Solid on the far left, liquid right here heating up, and then I didn't put gas on here because it would have been over here, but we couldn't take any temperature readings of the gas that was being produced because the thermometer was in the beaker with the water. So instead, we just have our condensation and evaporation / vaporization arrows. So if you're moving from right to left, you're going to have condensation to a liquid and then freezing to a solid. If you go from left to right, you'll have solid to melting and then a liquid heating up until vaporization, and then that produces a gas. So we want to think about those flat regions of that graph. Normally, when we heat something, it makes sense that it would increase in temperature the whole time, but that's not what we observed here. So we want to explain the temperature change, or the rather lack thereof, as the ice was melting. So I've given you two pictures to look at to maybe spur some of your thinking around this. Please write a prediction in your notebook, and then we'll carry on. So the temperature did not change because the thermal energy was being used to stretch the hydrogen bonds. So see these hydrogen bonds? They're being stretched so that the molecules can move around and be disorganized instead of being in this perfect lattice formation. So instead of increasing the movement of the molecules right away, instead it's stretching and weakening these hydrogen bonds so that the molecules will be able to move more freely. So that's why the temperature isn't changing. So let's think about our inter and intramolecular forces and what's happening to them. Make a prediction in your notes. What was happening to the intermolecular forces when the ice was melting? So the intermolecular forces are the hydrogen bonds, and they were being stretched and weakened when the ice was melting. Now think about the intramolecular forces. Did anything happen to them when the ice was melting? The intramolecular forces, which are the polar covalent bonds in the water molecule, remained intact while the ice was melting. And this is an essential point of a phase change, which is a physical property, right? It's still water. There's no polar covalent bonds being broken or made, and so that's why it's a physical change and not a chemical change. So the intramolecular forces stay the same. We also want to think about, why did it take so much heat energy to change the liquid water to a gas? When we had solid water, it only took about 10 minutes to get to the point where it was starting to melt and become a liquid. But once it was a liquid, it took a really long time to get up to where it started to become a gas. And when the experiment ended, we still had liquid water, right? So who knows how long it would have taken to evaporate all of the water out of that beaker, right? Our line would have gone on and on and on and on, and then eventually we would have boiled it dry, and all the water would have become a gas over here in the part of the graph that doesn't exist. Okay, so I want us to think about, like, why was this part of the process, heating the liquid and making a gas, requiring so much more energy than this little process, melting the solid, heating up the solid and melting it? Okay, so let's investigate. To do that, let's think a little bit more closely about vaporization. So explain the lack of temperature change during the vaporization of the water. So it looked like this, it was a liquid, and then it looked like this. Okay, so why do you think the temperature didn't change? The temperature didn't change because the thermal energy was being used to break the hydrogen bonds, not to increase the kinetic energy, so not to increase the movement or the temperature of the particles. So when it goes from a solid to a liquid, it weakens the hydrogen bonds, but the liquid water still has hydrogen bonds. They're just not as rigid. But when you vaporize water, the hydrogen bonds are totally broken, and the gas molecules can go anywhere. They just fly off to who knows where, and it takes a lot of energy to fully break that hydrogen bond. So let's think about what was happening to those intermolecular forces during vaporization. Make your prediction. And like we just talked about, right, the hydrogen bonds are being broken when the water is vaporizing. They're not just being stretched, they're being fully broken. The intramolecular forces during vaporization, what happens to them? Nothing. The intramolecular forces, our polar covalent bonds, remained intact when the water was vaporizing, just like they remained intact when the ice was melting, because the polar covalent bonds are really, really strong, way stronger than hydrogen bonds. And if we were breaking the polar covalent bonds, that would be a chemical change, not a physical change or a phase change. So that would be a really different type of situation. Why did it take so much energy to change the liquid water to a gas? It took more heat energy to change the liquid water to a gas than it took to change the ice to liquid, because during melting, the hydrogen bonds are only weakened and stretched, but during vaporization, they are totally broken. It takes much more energy to totally break the hydrogen bond. The formal language that we use to talk about this is heat of fusion. That's the energy required to change a substance from a solid to a liquid. In the case of water, that is 334 joules per gram. The heat of vaporization is the energy required to change a liquid to a gas. And for water, that's 2,230 joules per gram. You can see that's much bigger. It's a much bigger number than 300, over 2,000. That's why it took so much more heat and it took so much more time to start to change that water into a gas. Now let's look at kind of the opposite of what we just studied. Let's look at something cooling down over time. Here's what I'd like you to do. Draw this graph into your notes and answer these questions. What is the overall trend of the line in the graph? What evidence supports your claim? What is the temperature change between 9 minutes and 17 minutes? What is the temperature change between 17 minutes and 20 minutes? what are two similarities between this graph and the one from your lab? And what are two differences between this graph and the one from your lab? Pause the video while you do that. All right, let's do a little more analysis. Make a prediction. What do you think exists at this point in the graph? What phase, solid, liquid, or gas? We can see that the temperature is really high, and so I'm going to guess that this is a gas. So go ahead and label this section of your graph as a gas. So then let's look at this next segment. What phase change do you suspect is occurring at this point? Since we started out with a gas, I'm going to guess that this is condensation. The gas is starting to turn into a liquid. So go ahead and label this part of your graph condensation. I know it's a phase change because it's flat and there's no change in the temperature. Now we're cooling it down even further. This is going to be our liquid phase. We're cooling our liquid and getting it colder and colder. And then we get to this next plateau, which is another phase change. What do you think this phase change is? This is freezing. So it's going from a liquid to, of course, this last phase, which is a solid. And then we can keep cooling the solid down as far as we want to, and there won't be any more phase changes. Okay, so why do you think there are times when the temperature changes and there are times that the temperature stays exactly the same? We've already alluded to this. We're reinforcing this idea, so write your answer in your notebook. So the temperature stays the same during a phase change and goes up and down while the substance is in a phase, because the extra energy required to cause a phase transition is required to overcome the intermolecular forces, or to form the intermolecular forces between molecules at that point so that the phase transition can occur. So it's not really going to cause a change in temperature or movement of particles, because all of the energy is being used to either break intermolecular forces or form intermolecular forces. And that's why we have those flat lines on the phase change graph. Okay, hopefully this helps us think a little bit more about the data that we had in our lab, and this will hopefully also help you answer those analysis questions. Your lab is due tomorrow, and we will have a little quiz on Friday, as usual. Hit me up in office hours from 10 to noon if you need any help. Thanks, you guys.